It seems a simple idea. Take an electronic camera, connect it to a computer, and have a clever program figure out what's happening by analyzing the digital images. A simple but powerful idea. Not just eyes that never close. Imagine intelligent eyes that never close. Among many other applications, a vision system like this could be used for measuring, counting, monitoring, and controlling every step of the production process in a factory. The good news is that what should really be the hardest part, developing the mathematical algorithms to turn a picture into an observation, already exists. The bad news is that it almost always takes several weeks of calendar time and hundreds of hours to successfully deploy an accurate, reliable machine vision system. Or it has until now. Over the next few minutes, we'll show you how our open vision system allows you to install highly accurate and reliable machine vision systems in just a day or two. The way machine vision was always meant to be. We're going to need lights, lenses, and cameras to get the data, as well as computers to analyze that data and high-speed controllers to coordinate the whole thing. The system we've built allows us to draw from a design palette of thousands of components from hundreds of vendors to accommodate the breadth of vision problems we solve. Because our systems solve a world of machine vision problems, our systems can incorporate a world of components. But the work of all these components must be coordinated with events in the real world. Synchronizing the collection of quality images at the right time and place, then delivering those images at a different right time to a different right place without fail is the goal. So we've engineered this device called a Maestro to coordinate the imaging, decision-making, and delivery of answers from the vision system. On the machine side, we'll use an IE gateway as an extremely fast universal translator for PLCs. To handle the coordination, we designed software with drag-and-drop interfaces to control everything. Called Choreographer and Chassis, our software allows you to trigger the cameras, program sensors, assign tasks, and control inspections, all without writing any code. So our vision system can use lots of existing components, a few new devices, and drag-and-drop software. It can be applied to products as diverse as cells in a petri dish, components on a circuit board, apples in a cider mill, or parts on a production line. All we need now is a target. So what's on the menu today? Okay, we'll be inspecting game dice. But what would we like to know about them? 3 things: how they are oriented, how many dots are showing upward, and how wide they are. So far, so good. But it says here they won't be stationary. We'll have to catch them on the fly. So there'll be an unknown number of dice moving through our inspection zone that we'll have to keep track of while the images are captured and the calculations are done. That means we'll have to keep track of which dice have passed or failed the inspection at the same time we're inspecting other dice. Seems complicated. Welcome to the real world. How do we deal with this all too typical situation quickly and reliably? First, we'll use Choreographer to select and name the hardware needed for this project: cameras, computer, Maestro device, and an IE gateway. Then Chassis software will let us set up the cameras and lights to get the right images from each inspection station. We'll be doing 3 inspections in total: 1 for orientation, 1 for the number of dots, and a 3rd to measure the width of each die. We'll continue with Chassis to choose the algorithms we'll need to do the inspections and generate the answers we need. We'll need cameras to get our images. In this case, we're using Ethernet cameras from Opteon that also receive their power over the data network. Plugging one into our network makes it appear in Choreographer as an available device. We'll take this opportunity to name the camera Angle Cam because this will be the one that we use to find the orientation of each die at the first inspection location. Because this camera has the ability to drive its own lighting system, we'll connect a small but very bright light to the camera that will stop the action so accurate inspections can be done even if the die are moving very fast. In Chassis, we'll add a camera control and use it to open Angle Cam by name. Once the camera is open, we'll set up the parameters needed to get a high-quality image. In this case, a short exposure to stop the action and plenty of current for a bright strobe flash. Next, we'll add an event handler in which we can add a flow chart to perform all the tasks It should be done when an image arrives from AngleCam. We can now use AngleCam to take a sample image of a die to use in training the system to find the die and report its angle of rotation. To model a moving machine, we've mounted our target dice on a turntable that will move them past our inspection cameras. We can see that some of the die are aligned with the cameras and some are rotated. They also have various number of dots showing toward the camera. The job we're building will select or pass only die for which three things are all true. They are aligned with the cameras, have three dots showing, and are between 450 and 500 thousandths of an inch across. Here's the chassis flow graph for counting the dots on each die, and here for measuring their widths. Our system only needs to describe the inspections to be done on just one die, and it doesn't matter that several are passing through the inspection zone at the same time. Chassis automatically extrapolates the job to apply to any number of simultaneous or overlapping series of inspections. Because data is tagged from the very beginning with each die's unique ID, the vision computer always knows which images go with each die. This linkage is completely deterministic. There are no missing images and no escapes from the inspection process. So we have our moving targets, our inspection plan, our cameras and lights, and we've built our vision system with drag-and-drop software. How does it all work? First, Maestro is a very key component in our system. It's listening to a part sensor that detects when a die is approaching the first of our inspection cameras. The Maestro is also counting pulses from a shaft encoder on the turntable. When the part sensor responds, the Maestro uses the current encoder count to calculate when that die will arrive at each of our inspection cameras. When each die arrives at the first camera, AngleCam, the Maestro will send a packet over the network to trigger an image. When it arrives at the second inspection station, called PipCam, Maestro triggers that camera too, and so on for WidthCam. Because our system is so precise, we see that each camera fires only when a die is exactly centered in front of it. The Maestro is receiving pass-fail votes from the vision computer for each part and uses those same encoder counts to only trigger the fourth camera to flash a passing die with a green light. The image of the pass camera also allows us to see how precisely the system operates. Though the image looks frozen, it's actually live. The system precision of 1.2 microseconds represents just 1/7 of 1 pixel in a 1-inch field of view when the product's moving at 2,000 feet per minute. Put in other terms, that's 5 microns at 10 meters per second. This level of precision is 20 to 100 times greater than that required for even the most demanding production machinery. Truly seamless integration of vision and machinery is now as easy, as reliable, and as precise as you need it to be. We've designed the system's operation to be simple, allowing for easy deployment of the most complex vision solutions. We've engineered our system to be as hardware inclusive as possible. You can use nearly any cameras, any lenses, any light sources, and any Windows or Linux computing platform. It is also engineered to be open architecture. Algorithms from multiple machine vision vendors can be used together, and the results communicated to PLCs from all of the major manufacturers. Your machine vision plans can now be developed with drag-and-drop tools that provide rugged, reliable operation without writing code. VISICS offers seamless, sophisticated machine vision systems you can easily deploy in no time, and they're precise and reliable every time. To learn more about the VISICS Vision System, go to www.visics.com or contact us for your own personal demonstration.